Vehicle counting device.
Nowadays, traffic problems are increasing due to the fast-growing number of vehicles. That is why, traffic engineers are conducting a manual vehicle count survey in every road path that is experiencing traffic congestion. Counting cars is necessary in order to understand the density of cars on our roads, which ultimately helps traffic engineers and decision-makers in their planning and budgeting processes. Ensuring that traffic moves smoothly without a lot of manual intervention requires automated car counting techniques. These techniques include microwave radar, infrared or inductive loop detectors, as well as the use of traffic cameras. A computer vision-based system can also be a suitable alternative for car counting. However, this method is limited to weather conditions and natural light. We discovered that radar detectors are among the most economic and handy devices used for traffic surveys. That is aside from low cost and safest to install and to remove without traffic disruptions or lane closures. It is also not affected by the weather and light, unlike the video image processing and other sensors like infrared, ultrasonic, and passive acoustic. It has therefore become our best choice. However, it cannot classify the detected vehicles just by the vehicle length estimation. One hypothesis of a possible classification of detected vehicle is to write two different equations taking care of vehicle path distance from the instrument and the vehicle length, but this two-equation set is prone to errors, especially if the subject is in motion. That is why vehicle classification is not applicable. This is the statement of requirement of our study, which is to develop a vehicle counting device that collects the number of vehicles passing by on a certain location. It specifically requires to make a counting device using Doppler radar microwave sensor that collects the number of vehicles passing by, using motion detection. Build a gateway that will help the devices to send data to the Things network. Create a ThingSpeak channel that will generate reports of the following: a counter field that displays the number of vehicles passing by, and a bar graph that displays the summarized data from the counter with date and time. With VeCoDe, using RCWL0516 Doppler and radar microwave sensor is our way to count the vehicles. VeCoDe is a fully integrated unidirectional vehicle counting device, designed with a Doppler and radar microwave sensor and LoRa network. Featuring a small-size device, no-hassle field setup, one-person installation takes less than 5 minutes, non-intrusive sensing technology, long-range wireless connectivity and extremely low power, brought by the LoRa network, VeCoDe ensures operational safety during installation and data retrieval. VeCoDe is also connected to ThingSpeak Internet of Things Cloud, where storage is limited to 3 million messages per year, and also offers exporting of data in XML or JSON format for just 2 minutes. VeCoDe, combined with ThingSpeak capability, allows the device to automatically upload data right to your desktop. And reports can be generated from any internet-connected smartphones using the VeCoDe app. Data can also be retrieved locally, when necessary. For power and battery life, VeCoDe has a rechargeable 9V 600 mAh lithium battery that provides 2 to 4 days of runtime. Unlimited runtime is available using the Arduino USB power option. Based on the National Electrical Manufacturers Association or NEMA's occupancy motion sensors standard, the LoRa embedded sensor device should have an antenna opening angle of 12 degrees. On a unidirectional road, it can count vehicles through motion detection. As for this matter, the device must be installed on a pole at a distance from the carriageway between 0.5 meter and 2 meters, with an angle of 30 degrees towards the nearest vehicular direction, with a height of 1 meter above the road surface, anyhow not less than 1 meter and no more than 2.2 meter. The installation with an angle less than 30 degrees gives an overestimate of count, while an angle greater than 30 degrees gives measures underestimate. The accuracy of counting has been verified for the lane closest to the device, but it has not been reported for sake of brevity. This part of the video shows that the LoRa embedded sensor device and the gateway device are communicating on each other with the help of LoRa networks. To connect TTN to ThinkSpeak, the right API key, found on the ThinkSpeak channel, should match what is written on the Things network integrations, as well as the ThinkSpeak channel ID. In this counter field, we can see the number of count, we can also see here the bar graph that displays the summarized data of the counter with a certain date and time, and the location of the device. The VeCoDe leads with the conclusions based on the device development and several tests conducted. First, the developers were able to make a vehicle counting device using Doppler and radar microwave sensor, with Arduino Uno as the microcontroller with a Dragano LoRa shield attached to it. Second, the developers were able to make their own gateway device using Raspberry Pi 4 and LoRa concentrator board, to help transmit the data to the Things network, the network server of LoRa modules. Third, the developers were able to make a data channel from an IoT cloud application called the ThinkSpeak. The platform will generate reports in two fields such as a counter field, and a bar graph field that summarize the data from the counter field with date and time. The said channel can also display the status and location of the device. Lastly, the developers were also able to produce an Android app, where internet-connected smartphones can see the generated reports from the ThinkSpeak. Based on the results and conclusions, even though the use of IoT was possible and the VeCoDe sensor device and gateway device were functioning, the developers recommended the following for further development. First, the sensor device can be enhanced by the fusion of camera and sensor for vehicle classification. Second, the battery of the LoRa embedded sensor device can be recharged and run in an unlimited runtime using a solar panel with a solar charge converter. This recommendation is good if the device will be deployed to a location permanently. Third, the results of this study can be used as reference material for future researchers in the field of computer engineering and civil engineering.